Good morning, guys. We are starting a new unit. It is probability. A couple of quick notes. I did put on the website a blank copy of the entire notes for the whole unit. So you can, if you have a printer, you can print that all out now if you'd like to have it ahead of time. I also put a link for the homework so you could print all of them out ahead of time. If you have the ability to print front to back, awesome. Just keep in mind, you might end up with like the front of a homework on the back of another homework. So just be careful of that. Otherwise, I just wanted to let you know that that was there. And also, if you didn't get a chance to check out the announcements from yesterday, the 29th, just saying, might want to go take a look. They're kind of fun. All right, we are going to get moving here. First things first, probability. Okay, when we say like, what's the probability of that happening? You know, we kind of know essentially like what that means. Like, what are the chances? Like, what's the likelihood that it would happen? But this first little example, kind of interesting. I mean, it's a little when you stop and think about it, but it's talking about the mathematics of probability, saying obviously it's just observed things that we see happen. And it's saying, as an example, consider that you toss a single coin. So I'm right here. The number you might get could end up being saying you only do like 2, 5, or 10 tosses. So like you could toss the coin 10 times and get like 7 out of 10. But what we know is that if there's one head out of 2 sides, it should be a 1 in 2 chance that you end up with it, right? But that's talking about theoretical probability versus, why did my brain just shut off? Wait, I'm going to peek. Versus empirical probability. All right. So this example, it says you can't trust observed probability exactly because, you know, there's going to be variations. So it says in math, we imagine what would happen if you were to do it over and over and over again. So it's saying some amazing math heroes have tried. While imprisoned by the Germans in World War II, an English mathematician, John Carrot, tossed the coin 10,000 times. Kind of feels like what we're going through right now. You got nothing better to do, give it a try. It's saying the result was he got 5,067 heads out of 10,000, which came out to be about 1/2, but not exactly. So he tried to see like if he could get it to come out perfectly. And even then, it still wasn't, you know, quite 50-50. But there you go. All right. The vocabulary that you need to know. This is all filled in for you, so I'm just going to quick run through it. All right. What I want you to look at here, an experiment. When it says it's a process with well-defined outcomes, that example above is a perfect example. You toss the coin, it's either gonna be heads or tails. There's no like wish-washy stuff of what will happen, all right? The outcome is the single result. So literally it landed on heads or it landed on tails. An event, when it says a collection of one or more outcomes, that'll be when we talk about like what's the probability of getting heads 3 times, things like that, that we could consider an event, all right? The sample space, that's the list of all the possible outcomes. We're going to talk about that in terms of like tree diagrams or listing out like sets of points. The other thing that goes along with that, the sample space, can also be referred to sometimes as a capital S or capital U for the universal set. It's sometimes been called that as well. All right. The union of all sets, you can use the word or when we talk about the union. So it's the element of all sets A or B combined. Sometimes or people think it has to be one or the other, but it really means you're talking about like both. All right. So it's everything listed in both. All right. The intersection. Well, think of the intersection of the roads. That's where they would, you know, overlap. So the intersection are what elements they have in common, all right, that they share between the two. A subset is one set that fits inside of the other, all right? So like all the juniors at Fairport High School are a subset of all the students at Fairport High School. So it's just one group that fits in the whole thing. And then the complement. No, you're not saying something nice about the set. It's the idea, right, that they have to be in the whole sample space, so like all the students, but they're not in a particular set. So if I said, what's the complement of all the juniors at Fairport High School, it'd be everybody who's not a junior, like all the sophomores and seniors, all right? So everything that's not in that particular set. So that's the first part. Let's do a little example so you can see that a little further as to, can you pick out all these things? So they're giving you a little set A, which is 1, 5, 8, and 9. Set B, you can see here's 2, 5, 7, 8, and 9. A set C is 1, 7, and 10. Set D is 5 and 8. The sample space, meaning all the numbers, let's pretend that you could pick from that would go in there. That's your S right there. So as we practice it, I want you to look at the vocab above. So this is A intersect B, or A and B. So what that means is I just want to list the stuff that set A and set B share. All right. So what ones do they share? We'll look between the two. What do they have in common? They both have 5. They both have 8. They don't both have like 1 or 9 or 2 or 10, so we're not going to list those ones. So do your best curly bracket, right? And we would just list 5 and 8 in there. That's it. Right? For part B, B union C, this means we're going to list everything in both. We're bringing it all together. I actually like to think of the union like family reunion. We bring everybody together, all those random like aunts and uncles or cousins, right? So list everything in B, everything in C. Don't stress about the order of the numbers. So like if you list everything in B, 2, 5, 7, 8, and 10, and then everything in C has 1, 7, and 10, I can put the 1 and 7 on the end. I'm not going to list 10 again. Only list it one time. Mm-hmm. If it bothers you being out of order, then, get fancy, pay attention, and write them in order. All right. Next one, D complement. So that means it has to be everything in the big sample space that's not in this little set D. So since set D is only 5 and 8, you're basically going to take this whole sample space and you're going to remove 5 and 8 from it. So you're going to take those out, and therefore it would be 1, 2, 3, 4, 6, 7, 9, and 10. All right. The next one. Sometimes they get a little tricky, so you might have to think about them separately. So A union B complement. All right, that means everything in set A. So everything in set A would be 1, 5, 8, and 9, along with everything that's not in B. All right, off to the side here, B complement. What's everything that's not in B? Well, since B is 2, 5, 7, 8, 10, everything not in B would be 1, 3, 4, 6, and 9. All right, so if I do everything in A, so these were all in A, along with everything from this little set, well, 1 we already listed. We need the 3. 4 we need 6, and we've already listed 9. All right, there you go. So list everything that falls in those two sets. All right, last one. Is D a subset of A? So take a look at D. That's 5 and 8. Are both of those elements in this set over here? Yeah, well, 5's right there, 8's right there. So absolutely, yes. And when it says why, you can simply say, because 5, maybe I'll say 5 and 8 are in set A. There you go. So that is a really good example of helping you see like what do we mean when we say intersect versus union, complement, and subset. So there's your vocab intro for the unit. Right. As we move through, you're going to see some of like the probability stuff like decks of cards, or in this next case, the spinner. Sometimes we use kind of the basics to show our examples here, but it's okay because it makes it easy to follow. So for this one, it's saying basic definition of probability. If we talk about the probability of an event happening, we write it as a ratio. So the probability of E, the event, all right, would be N of E over N of S. Okay, what does that mean? N of E is the number of outcomes that fall into the event, so how many ways it can happen. N of S, that's the number of outcomes that fall in the whole sample space. So it's like everything that can happen versus just those events that you're talking about. It makes it sound really fancy when we write it like this, but it really is very simple. So try not to overthink it. All right, let's use this first example. It says we've got a spinner, 5 equal sections. So first of all, when it says, what is the experiment? Well, if I hand you a spinner, the experiment would be spin the spinner, all right, and see what it lands on. So the experiment would be spinning the spinner, right? And noting where it lands. So spinning the spinner and noting where it lands. Part B, give one outcome of the experiment. All right, if you spin it, tell me something that could happen. Right now, hopefully you're thinking like, okay, anything 1 to 5. So it says give one outcome. Pick your favorite number in there. If your favorite number is 3, there you go. There's an example of one outcome. All right, what is the sample space? I want to know what are all the possible things that could have happened. Well, it could have landed on 1, 2, 3, 4, or 5. That's your sample space. Mm-hmm. If you're not good at curly brackets, don't stress. I know you had some practice earlier in the year, but do the best you can. All right. What are the outcomes of the event of getting evens? All right. Well, even numbers, landing on a 2 or landing on a 4. So in that case, evens would look like that. Those would be the outcomes that we'd be interested in. All right. What is the probability of spinning an odd number, which can also be written as the probability of getting an odd? Well, the probability of landing on an odd number, well, there's 1, 3, or 5. So there's 3 ways it can happen out of 5 total numbers. Now you can leave that, as 3/5, or you can change it to 0.6. What I don't want you to do is change it to a percent. Even though we do tend to hear like, what's the probability of it's going to rain? Lately, it feels like 100%, but normally in math land, at least when we talk about probabilities, we really are just talking about it as a decimal value. Unless they say, what's the percent chance? Don't change it to a percent. Right? So when it says, what was the event from part E? Well, the event was right there, landing on an odd. What outcomes fell into that event? Well, that was 1, 3, and 5. And so then the last part, what is the complement of the even numbers? Well, complement of the evens is anything that's not even, or the odd numbers here. Okay. Now, something that we kind of naturally did, but we didn't fully show, was when we got the probability of spinning an odd number, that 3 out of 5, what was really going on there was the probability that it was odd is given as the number of odd values out of the total number in the sample space. There were 3 odd numbers, 5 numbers in the sample space. There you go. All right. So that's what I mean when I say don't overthink it. You can probably answer some of these without having to think super hard about it. All right. Down at the bottom, given the basic definition of probability, between what 2 numbers should all probabilities lie? All right. I want you to think about the probability of any event should fall between what 2 values? Well, over here, I want you to think about if it's never going to happen. Like it's a guarantee it can't happen. All right, what would that probability be? That should be 0. All right, and now it technically can equal that. So let's make that a less than or equal to. All right, what about the probability that it's absolutely going to happen? That is a guarantee. That should be 1. So all probabilities are going to fall between 0 and 1. Now, in terms of percentages, we'd say 0%, 100%, but I want you to leave it as 0 and 1 there. All right? So that's where I want your answers to be. All right, on this next page, we have another kind of classic example talking about marbles and colors of marbles and whatnot. All right, so let's see if we can move a little quicker through this. It says, let set A be a bag of marbles with various colors. The bag consists of 4 blue, 2 red, 2 yellow, 10 glitter marbles. Ooh. Set B, we've got 3 blue and 2 yellow. So that one's a bit smaller. So it says, what is the sample space of set B? They're basically just saying like, what's in the bag? Now, because we can't necessarily distinguish, you don't have to write it as like blue, 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 yellow, yellow. You could simply say set B is 3 blue and 2 yellow, and that would be fine. Right. Could you write blue, 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 yellow, yellow? Sure, go for it. Right. When it says what is in the union, of sets A and B. So that's A union B. Remember, union like reunion, everybody. So you got to list everything all together, all right? So when you put the two sets together, oh, goodness gracious. All right, what would we have here? We would have the 4 blue from here plus another 3 blue. So we'd have a total of 7 blue. Let's see, we've got 2 red here. We got 2 yellow and 2 yellow for 4 yellow. Oops. And then don't forget your 10 glitter marbles. Trying to picture those going like old school there. All right, what is the intersection? So what do they have in common? All right, well, between the 2 bags, what they both have, they would both have 3 blue marbles. So the intersection here, so A intersect B, they both have, yes, 3 blue, sorry, trying to read up top. And, ooh, they both have 2 yellow as well. So you're just listing out what do they have in common. Right? Next one, what set is a subset of the other? Well, which set has all the elements that the other one has? Well, that would be set B. So set B is a subset of set A. All right. So that's the subset. All right. Write down what a subset of B could consist of. There's multiple answers you could give. But if I wanted to list a subset of B, basically it's the idea that if B is 3 blue and 2 yellow, it has to be something that is smaller than this, less marbles than that. So you could say like 1 blue and 2 yellow. You could do 1 of each. You could just do 2 blue. There's so many ways to do it, but something where all of this would fit inside of there. Basically as if I gave you those and you just picked a few of them out. There you go. Last part. What's the probability of getting a red marble in set A? Okay, so let's think about it in terms of the definition. Probability of red would be the number of red marbles out of the number in the total sample. So I should say, oops, actually, let's say the number in set A. We'll write it like that. It's shorter. All right. How many red are there? Well, there's 2. How many total marbles in the first set? Yeah, 4, 6, 8 plus another 10, 18. So the probability would be 1/9. Right? Now, does that mean if you reached in the bag 9 times and pulled out a marble that you'd get exactly 1 red? No. All right. So what that brings up is what I mentioned a little bit earlier. That is the theoretical probability, saying like in theory, that's what should happen. That's the likelihood of it happening, all right? Versus an empirical probability. That's if you actually do like a trial and error and see what happens. Right? Let's straighten that out a little bit. So over here, theoretical probability, right, is the number, just like what we said on the last page, the probability of an event would be the number of outcomes in the event divided by the total number in the sample space. That's what that, N of E over N of S even means, all right? So like for the problem of, probability of a head, it'd just be 1/2. So things I need you to know here is you do not need to do an experiment to know this. It's what's called the long run probability. Right, that in theory, over time, that's what the probability should be equal to. Or it's the one that I will say, like, in theory, this is the probability of the event. And I know I write fast. You have the ability to pause me or go look at the notes online if you need to fill anything in. Right? As for empirical probability, it's still the same idea, right? But it's based off of observation. All right. So you actually do an experiment. And then you calculate the probability. There you go. All right. But in both cases, it has to be things that are easily measurable. You know, it can't be like, how do you feel about this? It has to be like, what's the chances of, you know, picking up the blue marble? It has to be things that can be calculated or measurable that way. Okay, we got one last page. I know first day, trying to get out all the basics sometimes takes us a little bit longer. Stay with me here, almost there. This last page is talking about a fair coin is flipped 3 times. The sample space consists of ordered triples, such as HHT, meaning like heads, heads, and then tails, which would represent the first toss being a head, second toss being a head, third toss being a tail. So it's in the order of which it happened, all right? Not random there. Then it says draw a tree diagram to show the different samples in the sample space. So you can list it or you can kind of show it. Now, tree diagrams can get messy if there's too many, like in this case, too many tosses. But if we keep it to 3 tosses, it's not super crazy. So if we start up here, this would be you. The first branches represent the first trial. So on the first toss, you can get heads or you can get tails. Then you're going to 2 more branches from each. This represents the second toss. You can get a heads or a tails, a heads or a tails. So right here, that's your first toss. This layer is the second toss, and then you're going to go one more time. So heads, tails, heads, tails, heads, tails. Right. That represents your third toss. All right. So that example that we just talked about a second ago, heads, heads, tails, that would be if we traveled this path. Heads, heads, tails. So all the outcomes are however many branches you have at the bottom. So when it says list all the outcomes as ordered triples, all right, it's slightly obnoxious to do this, but we'll do it this one time. Literally run every branch. So you can go heads, heads, heads. So H, 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 that would be the first outcome. Right? And now you can list it with the parentheses or not. That part doesn't matter that much to me. And then keep going. Heads, heads, tails. Go to the next branch. Heads, tails, heads. So H, T, H. And then it goes H, T, T. So I'm just working my way from left to right here. T, H, H. The next one would be T, H, T. T, T, H. And then T, T, T. Starts to sound like gibberish by the end. So you've got 1, 2, 3, 4, 5, 6, 7, 8 outcomes. So sometimes the advantage of this is it keeps it organized. Otherwise, you just start trying to like think of the different orders, it can turn into a big old mess. So now when it asks you find each of the following probabilities, it's actually pretty easy to do because you've got them all listed here. So the probability of all heads, well, there was 1 case out of the 8 total. Ta-da, done. Probability of getting exactly 2 heads. Well, exactly 2 heads. It happened in this case here, and this case here. So that was 3 cases out of 8 total. And then what's the probability of all heads or all tails? Or means you want to include both. So there was 1 case of all heads, 1 case of all tails. So there was 2 cases there out of the 8 total, or 1/4. So they're saying if you flip the coin 3 times, in theory, theoretically, 1 out of 4 cases, you'd end up with all heads or all tails. So, I mean, if you're bored enough today, give it a try. See if it works. All right. Are your answers in part C theoretical or empirical? These are theoretical. If you actually sit and do it yourself, that would be empirical. So this would be something that you would have to do. All right. And if anybody is bored enough and tries it, let me know how it goes. I'm curious. All right. Last question. Yay. A survey was done by a marketing company to determine which of the 3 sodas was preferred in a blind taste test. Any of you guys that have signed up for AP Stats next year, they actually do this in class where they do a taste test, and it's, I think, to determine, sorry, sipping my coffee there, to determine if you can tell like which soda is which. Like Wegmans versus like Pepsi versus what other stuff is there? Coke. Not that I'm the healthiest person ever. I just don't drink soda. It kind of grosses me out. As a kid, I thought it was awesome. Now I think it's disgusting. So I wouldn't probably be able to tell the difference between any of them because I don't know what they taste like. But there you go. If you take stats, enjoy. So let's see here. It's saying find the empirical probability. So it's empirical because this is actual data. They ran this little, survey and went off of it. So it's saying a person selected at random would prefer soda B. Express your answer as a fraction and as a decimal. Okay, so the probability that you prefer soda B, well, there was 24 people that liked soda B, and then out of the total 53. That's it. That's all you got to do. All right, to do the decimal, that's a little calculator work. So you'll be able to get through most of this without a calculator, but occasionally calculator will be helpful. So about 0.45. So not quite half the people is what you're looking at, like soda B. All right, find the empirical probability that a person selected at random from this group would not prefer soda A. So when we say not soda A, another way to write that would be A complement. So all the people that don't like A. All right, there's a couple ways you could do it. Since 18 like A, you could subtract 18 from the 53 and calculate it that way. Or you can kind of work ground up and say, all right, anybody that doesn't like A likes B or C. And so you could add together 24 and 11. And then out of that total of 53 and do it that way. Right? To 2 decimal places, grab our calculator here, 35 out of 53. So about 0.66. So those would be your answers there, right? And if we look, 53 minus that 18, there's the same way to get that 35 out of 53. So you can think of it either way. All right, guys, hope day 1 goes well for you. Make sure to stay on top of that homework. Have an awesome rest of your day.